Good morning, everyone. So we will continue from where we left off yesterday. We discussed how salt is produced in the field. Now, today, I'll probably tell you a little bit about how salt is purified to get it into that quality which is required for some of these industrial products like making soda ash or caustic soda chlorine, which we'll discuss later on. Typically, the salt that you get in the field, even if you do it very carefully, will have something like maybe in the best of circumstances around 96% purity. Because these other constituents are building up, they are highly soluble in water, so they don't come out. So there will be adhering compounds like magnesium sulfate, magnesium chloride, which will always be there in the salt. Even gypsum has this characteristic that its solubility actually goes up as the sodium chloride concentration goes up. So it's very difficult to effect a clean separation between gypsum and sodium chloride. So some amount of gypsum always remains. Part of it could be that it is suspended material which just stays along with the sodium chloride, and part of it could be things which are crystallizing as you are going along. This is one of the most traditional technologies that is used to refine salt. Like you can see, it goes to these conveyor belts, and on the right you have got these vast heaps of salt which need to be upgraded, and on the left you see the salt after it has been upgraded. Of course, this only tells you that it just looks whiter, which is the normal color of salt. As you know, it's white in color. But it's not just the color. Actually, impurities also get removed in this process. Now, what happens is that there are two kinds of impurities that are present in the salt heaps over here. One is, as I told you, it could be suspended material, like particulates of gypsum, or because it's an open field, sometimes there's a lot of wind, and there'll be solubles like clay matter, etc., which deposit in the crystallizer bed. There's nothing you can do about it. I mean, it will be there along with the salt. So what this is called a washery. There are two parts to it. One is that I wash it with a saturated brine. Saturated brine means no salt as such will dissolve in it because it's already saturated. The salt and this brine, they are nicely agitated in the screw classifier. What that does is that in the process, the suspended materials get removed. That's one thing that happens. I have not showed you the clay matter, but you can see like gypsum, it's come down from 0.87 to something like 0.53%. Still high, nonetheless, it's reduced quite a bit. Some amount of magnesium sulfate and magnesium chloride will also come out when you do that. But there is always some impurities which are binding crystals of salt. And I'll show you that later on. Those things, are very difficult to remove with the saturated brine. So what you do is that you take a slightly undersaturated brine so that some amount of salt will actually dissolve, and in the process, it may expose a large amount of impurities for removal. You may not have much of a loss of salt, maybe about 10% or thereabout with the loss of NaCl because you've taken an undersaturated brine. But then it's required because quite a bit of the impurities can get out, which otherwise is difficult to remove. And then what happens is that after you have done the 2 stages of washing, then it is again taken in this conveyor belt where all the adhering moisture is sucked out. When I say all means you'll still have about 2 to 3% or maybe up to 5% water present in the NaCl. But most of it is removed, the moisture, and then you may choose to crush it into a fine powder, and then it can be used directly. It's fed, transported by truck or train to various places, and then it's used downstream. As I told you, roughly about 80%, 75 to 80% of the salt is made in Gujarat. And imagine when you have to transport things from the west coast to, let's say, the east coast. Okay, a lot of exports also, and so obviously you have to minimize things like moisture, etc., because you don't want to unnecessarily transport water. So those are the ways in which you can purify, and this is a very traditional way of doing this purification. There's nothing better as far as at least the suspended materials are concerned, like clay matter, etc. I mean, this is a good way of taking those out.
So,
Yeah,
so sorry to interrupt you, sir. But can you please explain why unsaturated brine is added in the second screw, one side?
sure. You see, what happens is, what you have is a lot of small crystals of NaCl which tend to get glued together. Now, what happens is that the glue in between is not NaCl; it's some other impurity. You know, so by taking an undersaturated brine, what happens is that you disrupt the surface. Some amount of NaCl gets dissolved, and it loosens this dirt, which is this gluing agent, and it therefore tends to get released. Is that clear?
Yes, sir. Thank you, sir.
Okay. You know, I showed you those ladies working in the salt field. There's a huge difference in the price of pure salt and very pure salt. When I say huge difference, it can be a factor of 2 to 3 or maybe even more. You can imagine that if we know how to make very pure salt, ultimately these people, laborers who are working in the fields, etc., naturally they'll also get some money, and also the downstream operations become less complex. In India, what has been up till now going on is that what the government and everybody allows is this grade 2 salt. Grade 2 means that it has to have 98.5% minimum sodium chloride. Okay, I mean, and there's a specification of all the different impurities like insoluble matter, calcium salts, okay, as calcium, magnesium, sulfates, iron. So all these things are specified. We also have a specification for grade 1 salt where the minimum is 99.5%. But until recently, nobody was really making it, because with their conventional method of making salt in the field and then upgrading with a washery, this is the best that they could achieve. But you can see, I mean, I've just given it for different countries, and you can see that their impurity levels, you can see NaCl 99.6, 7, all of them is quite high. Most of them are more than 99.5%. And these impurities tend to be a lot less than what we have in our grade 2. You can see 0.6% weight by weight sulfate, and most of these are 0.16, 0.17, etc. And this, just that 1% difference in purity, or 1 to 1.5%, can make, as I told you, a difference in factor of 2 or 3 in the price. So obviously there is a need to make the salt as pure as possible, and especially in a country like India, which makes something like 35 million tons of salt. It's not so critical, some of these impurities for edible application. Okay, in fact, some of these nutrients like magnesium, calcium actually could be helpful for us, good as a micronutrient in the body. But that's not true for industrial applications. In industrial applications, you need to minimize them to the maximum extent. And just to give you an idea, about 60%, 60 to 65% of all NaCl is consumed for industrial application, and about 35% goes for edible application, including making iodized salt and all the stuff. because one of you asked the question, I think it will probably be easier to explain to you. Although the picture is not so good, this is the kind of picture that you get when you take the NaCl from the field. Even before the washing, you're just making heaps and getting the NaCl. If you blow it up, what you'll see is, yeah, you can see it here, many tiny crystals. Can you see many small crystals which together are forming a large crystal? It is in between these small crystals that many times these impurities can reside. It's very important never to take anything for granted. Never assume that just because salt is something that has been produced for hundreds of years and what can you possibly do to improve technology, then of course you'll never improve anything. Tell me one thing, why do sometimes you get very small crystals and sometimes large crystals from the same type of solution, same kind of compound? You can vary the size of a crystal. Can someone answer to me why that is the case?
Sir, it may be dependent upon the heat provided by us during crystallization.
These are all done under solar evaporation conditions. That probably will be somewhere in the range of maybe around 30 to 40 degrees centigrade. Typically, in the summertime, maximum 45 degrees, not more than that. That's not really within your control. Anything else? Why things are sometimes small and sometimes big? When we saw this and we realized that there are impurities at the boundaries, we did something extremely simple, whereby we were able to make the crystals larger. You can see these look more like blocks of ice, so bigger crystals than in this particular case. And it so happened that the impurities were considerably less in this crystal, simply because there were not that many grain boundaries. The total surface area covered by grain boundaries was less. Okay? So the impurities absolute quantity was less. But what could we have possibly done to convert from something like this to this? Or what would you think of?
Saturation.
Saturation, that's good. Of course, the salt is coming out only after you reach saturation, right? As I told you, NaCl solubility doesn't change much with temperature, whether it's 30 degree or 40 degree. Once you have reached saturation and you are evaporating more water, then necessarily the NaCl must come out. You are really already operating at a saturation point. Although it's a good point that you're making, that there could be technologies whereby you might be able to do something like, say, salting out of under unsaturated conditions. That's possible. But in a field, normally you will reach the saturation point, and only after that the NaCl will come out. Any other thoughts?
So, depending upon the water present.
Water present, again, as I told you, I mean, the yes, water, of course, is evaporating continuously, and the salt is coming out. All your other impurities are, of course, building up. That's a very good point. Like, for example, suppose I keep evaporating and try to extract most of the salt. Okay? Obviously, my impurities will build up more, because they will be continuously, linearly, almost increasing in the mother liquor, and naturally in the wet salt there will be more impurities. So yes, to that extent, water content is important. That if you have less water content, then proportionately impurities will be more. But I'm asking in terms of the crystal size. What causes something to crystallize?
Sir, we can, when the solution is supersaturated, we can also add a certain crystal externally, and then it starts clumping.
Yeah. Have you heard of nucleation? So basically, there would be methods of inducing crystallization, causing differences. Like, for example, you remember the field, and I showed you the pre-crystallizers and then the crystallizers. Now, what happens is that in the pre-crystallizers, by which time most of your gypsum should have separated out. It does, but some amount always remains suspended. Or, as I told you, there could be clayey matter from wind which can get in. And so, what happens is that there are many of these particles which are present in the brine. It's not crystal clear. In fact, it will be slightly hazy, cloudy. The primary size of these crystals would be dependent on the number of nuclei around which these crystals are formed. So, if there are more nuclei, the sizes of the crystals would be smaller. And so, if these very fine suspended material, such as dirt, gypsum, etc., can act as nucleation sites, then of course, it might lead to very small crystals, and that could be the reason why you have these very, very tiny salt crystals that you see on the left side photograph. How can you make a solution which is hazy, cloudy into clear?
We can add alum.
Wonderful. Wonderful. You can add alum. And believe it or not, that's exactly what we did, and which led to a breakthrough technology. You're so right. Just before putting it into the salt crystallizers, the brine was just treated with alum. And when I say alum, means I'm talking about 10 to 20 ppm. You're not talking about dumping huge amounts of this stuff. And you know that alum is very effective for flocculation because of the Schulz-Hardy law, where it goes and sits on the surfaces, and that interaction energy almost goes as the proportion cube of the charge. So if you've got a +3 charge, it will become 27 times more effective than something which is +1 charge. And so by that very, very simple technique, one was able to make a crystal clear brine, and the salt that came out from that was very, very pure. We had more or less reached these levels. There was only one problem which we faced, which was that in all of these things, you'll see that the calcium concentrations are typically higher than the magnesium concentration. And higher or equal, very, very few cases like Spain, you can see it's reverse. But most of the people who subsequently practice things like solvay process, etc., and have to do some downstream refining, they always prefer close to a 2:1 ratio of the calcium and magnesium. And I'll explain to you the reasons for that later on. And so we found a situation more like this Spain stuff, that it was 0.05, 0.11, which these companies told us, it's great stuff. Never ever have we got such low levels of impurities. But if you can reverse the calcium magnesium impurity ratio, that would be even better. It is not that there is no grain boundaries and impurities. Even here, there will be salts, etc., with particles which are glued together. So we looked at what is the glue. What actually happens when we did a infrared analysis. Now, this is another thing. When you are producing these things in the by the millions of tons, and all these guys who produce salt, they are okay, they are practitioners in the field, but if you go and tell somebody, hey, why don't you put your stuff under the microscope and see what is there, they'll say, microscope? We produce millions of tons of salt, and what are you talking about? But honestly, the clue came just by putting the salt under a microscope and seeing what's going on. And by doing an infrared spectroscopy, this particular peak revealed a lot. What it revealed is that there is fair amount of what is known as magnesium oxychloride. This particular wavelength is very characteristic of that. And we said, oh, magnesium oxychloride is known as a cementing agent. It somehow likes to bind things up. Now, what happens? Suppose I take magnesium chloride, which is present in brine, and if I start increasing the pH, what will I get finally when I have made the pH quite high from magnesium chloride? If I add alkali to it, what will form?
MgOHCl.
No, at the end, when I've added quite a bit of,
Hydroxide, magnesium hydroxide.
yeah, you'll form magnesium hydroxide. So obviously magnesium hydroxide just doesn't form straight away. As I'm raising the pH, there's an intermediate point where you'll form these kinds of compounds like magnesium oxychloride, maybe around pH 7 to 7.5 or thereabouts. And if I go still higher pH, I will form magnesium hydroxide. But obviously brines are more around close to about a pH of 7. So it's not surprising that they form magnesium oxychloride. Now, if I knew that magnesium oxychloride is there, as we find out from this infrared spectrum, and if I say that I should try and not form it, then what should I do? What should I try and do?
Making it slightly acidic.
Wonderful! I am so happy. I'll just put student. All answers given. 1. Add alum to reduce turbidity and hence undesired nucleation. 2. Make the pH slightly acidic. That's it. There are 2 US patents granted for this. The 2 things that you mentioned, and you can see by reducing the pH to something like maybe a pH of around 5.5 to 6, you can actually almost make it disappear. And exactly as was thought. Now what happened was that the calcium magnesium ratios became perfect, roughly that 2:1, and you get of course a very low sulfate, and so and the NaCl concentration was greater than 99.5. So effortlessly in the field, mind you, without doing anything else, that one could comfortably achieve these kinds of specifications. And so the value of the salt has, you can imagine what it did and what it means also downstream in terms of reduced level of purification. So this is something like a technology which has been known for hundreds of years. You have to ask yourself, yeah, okay, fine, but what's the point in saying that? Can I do something about it? Now, I don't know how exactly these people reach these levels. Maybe they are doing the same thing that we were doing, or maybe we accidentally discovered what they are doing is possible. Maybe they wanted to keep it as a trade secret, and so they did not patent it. But nowhere in the patent literature was this known. So this has become India's technology. And today you can make grade 1 salt of exceptional purity. By the way, this is a trial carried out in Grasim Industries. 10,000 ton trial with both of those. First you do clarification by alum, and then you do a slight pH adjustment. Now you can work it out sometime in your spare time at home. You see, I mean, you might say, what? When you are you've got these giant salt fields and you're going to put acid there? Is it practical? How much acid would you require? that's where your knowledge of chemistry is important. You know that a pH 7 means 10 to the power minus 7 molar of H plus, and pH 6 means 10 to the power minus 6 molar. That's the difference that I have to put. That's the amount of acid that I have to put. And so what happens is it becomes a negligible amount of acid to put for a large field, maybe measuring something like 100 feet by 50 feet. You may just have to put less than a small bottle of acid in. That's it. And just to give you an idea, the cost of adding alum was added about maybe 1 rupee per ton of salt, and the acid maybe it added another 2-3 rupees per ton of salt. So per ton. So that becomes such a trivial expense, yet you get a huge impact. This is a great technology for removing impurities which are present at the grain boundary, and also some of the suspended impurities. But you can have impurities which are lodged deep inside the crystal of NaCl. In which case, those technologies will not work. That's not going to help you to remove those impurities. There, what you will need to do is a recrystallization of NaCl. Suppose you have got those kinds of impurities and they're very critical, and you need to remove it. And you say, look, I have done everything. Like, for example, we could remove all the traditional impurities, but a company came and said, can you remove bromide? And we tried, much as we did, we couldn't buy that technology. So at that time, we had no choice except to think that we'll have to do a recrystallization of the NaCl. What's the problem in doing recrystallization?
So we may lose some amount of NaCl again.
Yes, that is one. You may lose some amount of NaCl. What else? That's the least of the problems. Some amount is okay. What else?
So increase the cost.
Yeah. Why?
So because you have to recrystallize the NaCl again, so you require more labor, etc.
How would you recrystallize?
Sir, in some special equipment now.
Special equipment. Like what? Dissolve and then strip off the water. Is that what you're saying?
Yes, sir.
Yeah, then you can imagine that if you're going to do it by artificial means of energy, that there would be a huge energy cost, right?
Yes, sir.
If special equipment is used, for forced evaporation, then there would be a huge capital cost and operating cost. Right?
Yes, sir.
Yeah. Do you think it's possible to recrystallize in the field? After all, we are making salt that way, right?
So wouldn't the fact that it is very concentrated already make it difficult to go through the process again?
No, you are taking the NaCl and you have to dissolve it. And then you just leave it again in the pans. And in fact, it being very concentrated is an advantage, because then I'm not starting from seawater. You see, then I'll have to remove tons of water. I'm only having to do the last part of it.
So is it possible that the pans which are already containing seawater for evaporation, we could add the extra salt in them for recrystallization?
Where will you add it?
So already there are salt pans which have seawater which are kept there for evaporation. So can we add the salt again into those?
Brilliant. Yes, you can. Dump it into the seawater. Now, seawater is not pure water. It's got impurities. So one doesn't know. See, I've gone through the process of removing all the impurities. Now, if I again put it in seawater, I don't know whether I'll make a bad problem worse. It's also possible, right?
Yes, sir.
Yeah, so, but dangers. Okay, now this is another thing. If, for example, when you are taking seawater, and what did we find? That by the time you have produced salt, your water levels have gone down by 97%. So obviously the impurities in seawater are very small. And what am I doing? I'm putting all the NaCl in. So now when I evaporate, I'm not going to evaporate 97% water, because I'm going to now make a saturated solution of NaCl in seawater. You understood? But even so, unless you do the experiment, it's very difficult to tell. But again, can you believe it? That for something which has been practiced for so many years, hundreds of years, that no one had ever done recrystallization of salt in an actual solar pan in a field. Hard to imagine. In fact, these patents were granted. They said, yes, nobody has done it. And you're saving such huge amounts of energy. And also by using seawater, I didn't even require fresh water to do it. Although it would have been better to do it with fresh water, because maybe you could have made a super pure salt out of it, because those impurities in seawater would not be there. But even so, look at this. Okay, look at what has happened to the impurities. They have become vanishingly small. And this was a problem because it was lodged inside the crystal. So you couldn't take it out with those earlier technologies of alum and acid. But by doing a recrystallization with seawater, okay, you could make it less than 10 ppm. You might say, why is it so important? Can anyone tell me why this company, some company, why were they so interested in having a NaCl with low bromine?
Probably because bromine interfered with the reactions.
Which reactions?
I don't know, sir. Whatever reaction they were carrying.
Very good. What I like is that you're thinking logically.
Ammonia soda process.
Ammonia soda process less critical. I'm not saying it's not important, but it's less important. Where else are we going to use it? The NaCl. Another big application where NaCl is used?
HCl production.
HCl.
So sodium hydroxide production.
Yes. Caustic soda chlorine. Now,
Yes,
when you produce caustic soda chlorine, because the bromide is more easily oxidized than chloride, in my chlorine, I will always get bromine, because I'm doing a electrolysis process. How am I getting chlorine? I'm getting it by oxidizing chloride to chlorine. I can take molten NaCl. There also it will be the same story. Or I can take it in solution, which is what the chloralkali process is. But in either case, because bromide is more easily oxidized than chloride, I'll say because bromide is more easily oxidized than chloride, chlorine will have bromine. And you know what? See, these chlorine, etc., are used, for example, to make chlorofluorocarbons. They are used to make all kinds of refrigerants. And the most damaging is bromine, because the CBr bond is the weakest. So it actually participates in these radical reactions much more than the CCl or the CCF bond. And so this destruction of the ozone layer happens the most when you have got any compound which has got CBr, and that's why it's banned. And it is that which was the concern. Look, when you are doing something and to be able to relate your work to the destruction of the ozone layer, and then on the other hand to relate it to salt production and say, hey, I reduced bromide and I've actually made a positive impact on the ozone layer. That's great. Don't see these things as low tech. They're all part of the chain, and believe me, They're extremely high-tech. Any of these so-called technologies which look silly doing in the field, there's nothing silly about it. Okay, so we did it in the field. What would be the one problem of doing it in the field? Let's say, even if I manage to do it with seawater, or it is desirable to get it with fresh water, in which case, in these areas, you are not going to get fresh water to do recrystallization. Maybe if we had done it with fresh water, we could have made this virtually zero. Okay, I don't know. We never tried it, but it could be. What else would be the problem? So one is that we are doing it with seawater, which could be a potential problem. There are other problems. Let me tell you. By mistake, when I am doing, my recrystallization, if some of these impurities are going to my brine, or by mistake some very high concentration of sulfate, etc., there are dangers. So we have to be a bit careful. But what else would be the problem in doing it in the field?
Sir, transportation.
No, I'm still in the field. I'm not transporting anything.
So stirring, mixing the solution again.
Stirring. There are well-known methods of doing stirring in the field. There are people who use paddles, and you can do it. And you see, it's not like a factory. Residence time is not so critical. I don't have to dissolve it in 5 seconds. In the field, I don't care. Even if it dissolves in 1 hour, I'm okay. Things which are very critical in the plant may not be so critical in the field.
So will require manual labor and will require a lot of time.
Lot of time. Okay, suppose I want to do it in the same time, then what do I need more of?
Land.
Yes, that's it. Land. I write these things, I hope you'll understand what it is. Manpower and land and lack of fresh water, if critical. Okay, let's put
yes, sir.
Constraints. The great thing is that once you identify a problem in a very, very sharp and focused way, you can always go looking for a solution. What I want you to do is, you'll have a few days to think over the problem, and we can discuss it on Monday. Okay, and I want you to ask, there are two questions. Let's not talk about the labor part of it, but let's look at the lack of fresh water. Suppose it was important, and I said, no, let us try and do recrystallization with fresh water, and the requirement of more land. So take these two. Now, can you think of any solution which can help to reduce or eliminate both of these? I hope that one of you on Monday, when we start the class, will provide an answer.